Back. I'm glad to see all of you here. I thought I may have scared too many of you with what we covered yesterday, but I guess I didn't. So that's great. Um, so I just have some quick comments before we actually get started. So first, just want to go through some of the things that we talked about yesterday. We talked about R and R Studio and why I think R is such a great tool. We talked about some of the nomenclature that R has, so object, argument, package, and all those things. So we spend a whole bunch of time doing data wrangling. And just something that I want to stress that maybe I didn't enough yesterday is, probably all of the data wrangling things that we did yesterday, you can possibly do in Excel if you want, but it's going to be copying and pasting, dragging and doing all that. And that's really prone to human error and you may not even realize. So the example I was given yesterday about this research group at Duke University is, again, they came up with this algorithm to predict what type of treatment would be best for a patient with cancer, and they published it, and then a different group of researchers actually asked for the data and asked for them to tell what analysis they did so they could try to replicate the analysis and the results, and they never got to the same results of the second group. So they realized that the group at Duke actually made a whole different number of mistakes, both in the analysis and on the data wrangling part that we're doing manually some parts, that caused analysis to be flawed. And nobody would have known if somebody else hadn't checked it. So we're talking about here this data wrangling steps that it's mostly for you to try to get away of touching your data too much in Excel and bringing to R or any other software that you can do that reproducibly, right? So you still have your raw data, but then you're going to start using all these functions that are not only automating it for you, but also when you write code, you are writing down what you're doing. So you have a record of what you did to that data. And at the end of the day, we exported, so we brought this data set in that was kind of messy. Then we wrangled the data and we exported that data yesterday at the end of the day. And that's what we're going to start using today for the analysis. So I know that we didn't have too much time in between last night and today, but I just wanted to ask, did anybody try the challenge that there was at the end of the script? Carlos tried. Were you able to get it done? Awesome. So, it's really, these 4 hours that we're going to have here are really compact, really dense. The idea is not for you to come out of here with advanced knowledge in R. It's more for you to know what is out there. So if you really need, you know how to search, you know where to go to find help. And it's really important that if you want to keep learning, you have to just keep investing time on this and forcing yourself to do stuff in R. And Google is your best friend for this. Many times for me, I find that if I can ask the right question to Google, I get the right answer. You may need some studying on my part, but in the end, you start realizing that you can learn a lot on your own once you know the starting point that we had yesterday. Okay, so today we're going to start running a randomized complete block design analysis of variance. After that, we're going to check model assumptions, extract the means of the model, perform pairwise comparisons of those means. They're going to create a plot with those means, the letters, everything very pretty. It would be basically publication ready. And that would be the first hour. The second hour, we're going to use the same data set, but instead of running ANOVA, we're going to run a regression, which is very similar behind the scenes, but it has some different results in the end. And depending on what your role is, you either want to use ANOVA or regression. And the last thing we're going to see is how we can automate repetitive tasks. So let's say we're going to have these 4 locations. How can we run a whole bunch of things, write the code only once for one of them, but make it work for all 4 automatically? So we're going to take a look at that. Okay, so before, maybe you have done this already, but if you don't have the project file open, like the project icon open here, so if up here is not saying, if you're seeing project none, is because you're not within your project. So for you to get in the project that we created yesterday, there are 2 ways. One of them is if you just open R Studio and you click, let me just get this out of the way, and you click on that down arrow, is going to show you a list of projects that you have already created, or the last 10 ones that you used. So you can just click in one of those if you want to launch the project that we created yesterday. Another way is, if you think about it, like currently I probably have, I don't know, hundreds of different projects that I created over time. So if I want one that's not in this list here, you can also go to the folder. Let me just minimize this. So this is my folder from yesterday. So if you guys created that project inside this folder, there is an icon there, and you can just double click this icon. It's going to open that project for you. So you really want to make sure that you have this project open when you start. You don't want to have the project none on the right corner, because if that's the case, all the paths for when we're importing and exporting things are not going to work properly. So make sure that you actually open the project and not just an empty RStudio window. Anybody having trouble with that? Okay, so we're going to move on then. Okay, so in your script, this is the one that I share with you, which has a whole bunch of blanks that we're going to be filling up. There is this first line here that's to use that function that we saw yesterday to install packages, and we're going to install the broom.mixed. So if you have not done that yet, please go ahead and run this to install this package. So here, right after that, you're going to see that we have this setup chunk where we have a whole bunch of library functions and package names inside of those functions. So this is what we were talking about yesterday, that you basically install a package the first time and anytime you want to update that package. But if you're just trying to bring that package and make it active for that R window, you want to use the library function, not the install packages. So the library basically loads that package into your R session. So here I already left for you all the library functions there with the package we're going to be using today. If you want to go ahead and run it, and it's probably going to give you some text below here. That's mostly because Tidyverse has a whole bunch of warnings and just lets you know of what's going on behind the scenes. But if you want to go ahead perhaps and like put your cursor anywhere in the first row and just hit Control Enter, and then that runs one by one, because in that case, if any of those packages have not been installed for you, it's going to give you a red sign instead of that green. It's going to be red, and you're going to be able to see what is it that you don't have, and you can go ahead and install. So is anybody missing a package at this point? Okay, it doesn't seem like it, so we're gonna move on. Okay, so the first thing we have here, the next chunk we have here is for reading data. So I want to call this soyk_w, which is already there. I want to use the assign symbol, and we're going to use a function the same that we used yesterday, read_Excel. And now this is where being in the project and having saved that Excel file from yesterday on the data folder makes a difference. Because now you come here, you open and close quotation marks, put your cursor in between the quotation marks and hit tab. That's going to show you the path. So right now we are inside the notebook notebook folder, subfolder. To get outside of that, we use ... and / on Macs. Perhaps on your PC, on your Windows could be /, so you can try that if the forward doesn't work. And now we're outside of the notebook folder. We are seeing the entire project folder. So we want to get into the data. So we go into data and already populates for us. You hit tab again. And at least I'm seeing 2 files. You should be seeing 2 files as well. So you should be seeing the soybean workshop, the one that we started yesterday. So this one we don't want to use today because we already did all those data wrangling functions to it. We actually want to bring in the soybean workshop processed, which is the one that you should have saved at the end of yesterday. So we bring that. This one only has a sheet, but if we just want to keep consistency, we can just say sheet equals 1. So it's going to bring the first sheet of that Excel file. And you can run this piece of code here. So for me, it imported. I can see that soy K object up there. And if we, on my environment, and if we just want to check what's inside of it, we can just print it below this chunk and see what's in there. So this is exactly what we had yesterday, at the end of yesterday. This is what you want to have at this point. Does anyone have an issue at this point? Okay, so we're going to move on. So now that we brought this data set, let's just do some visual exploration of what's going on, right? So just to remind you, it's a randomized complete block design study. The treatment design is basically a one-way treatment structure with potassium rate as the only treatment variable, and it has 4 levels: 0, 50, 100, 150 kilograms of K2O, pounds of K2O per acre. And it was repeated in 4 locations, right? And then what was measured, what we have here in this data set, is basically the potassium concentration of the whole plant of a given sample for each plot at R4 growth stage. So just to refresh your mind of what we have here, what we want to try to look at. So let's start with box plots. We're going to be using ggplot throughout the entire workshop. Just is what we started using yesterday. We're going to be using that same logic as far as thinking of how we can assign color and shape, and how we can just make it more visually appealing for us to understand what's going on. So if you recall, ggplot starts with the function ggplot. The first thing you give it is that data argument. So in our case, it's soy K underscore W. You can add a comma after that. Now we're going to call the AES function, the aesthetics function. So in that, we're going to say what goes on X, what goes on Y. So for this, if you recall as well, there was this other function that's called names that we can use with the object soy K underscore W. And that's going to tell us what are the column names that we have in this data frame. And that way, we can just copy and paste on our ggplot call. So let's go ahead and put K rate, kilograms per hectare, as our X. So X equals K rate, add a comma. And our Y, I want to be the K percentage. So Y equals K percentage. If you just run this piece of code here, you should see just that empty canvas. And again, the reason why there is nothing in there is because we haven't told ggplot how to display that information yet. So we do that by adding a plus after the last parenthesis here, hit enter, and now we're going to use a geom that's called geom underscore box plot. Okay, so it should look like that. So if we run it now, we're going to see a big, ugly box plot. So first off, does everybody here know what a box plot means? What is it showing? If you don't know, please raise a hand, because it's very quick to explain. Okay, thank you. So a box plot basically is showing the distribution of your data. So the idea is that the line in the middle is the median of the data set. Then the 2 edges of the box are the lower is the 25th and the top is the 70th percentile of the data set. And then the whiskers, these lines here, they extend to a certain distance away from the 75th quantile. I don't remember what is that distance, but it's something related to the standard deviation. And the default that ggplot uses is in the documentation. If you want to learn more about what is that distance, you can just look for it in the documentation of ggplot. And if there is any outlier, which means that is even a data point that's so away from everyone else, it's going to show a dot somewhere. So in this case here, there is no dot. Okay, so let's just stop for a second here and think about it. So we did say that we wanted potassium rate in kilograms per hectare as the X, and it basically grouped all those 4 rates into one big box plot. Why is it doing that? Basically because box plots are useful for categorical variables, which in R we call factor. So if we just come up here again and to our data set, we can see that K rate, kilograms per hectare, is being interpreted by R as double, which is numerical. So if we want to have 4 distinct box plots there, we have to do something with this variable and make R see that as a factor instead. So we're going to move. Let's do this. Let's first copy this first call to ggplot that we did. Just copy that and paste on the chunk below. And now there is a quick fix that is helpful on the go that I want to show you how to transform that variable into a categorical variable or a factor, which is to use that function factor. So I just came right before, I just came right before the K rate that I had as my X, and I introduced the function factor. So I wrote factor, open parentheses, had K rate underscore kilograms per hectare inside of it, and then I added an extra parenthesis that was not there. Don't forget this parenthesis here, because otherwise your code's not gonna work. So if we just run this piece of code now, okay. Now we're starting to see some more box plots there. So now it basically, so before K rate kilograms per hectare was a continuous number. That's how R was seeing it. Now R is basically seeing those as categories. I mean, it is still saying 0, 56, 112, 168, but it could just very well be A, B, C, D. For R, it would make no difference. Now they are categories. The number is just, it doesn't have a numerical meaning anymore on the x-axis. And that's why it actually created those 4 different box plots. So now I want to ask you to copy this ggplot that we just wrote and move to the next chunk. Just paste it there. And what I want to do is inside box plot, I want you to write that AES function. And then let's say fill equals location. So before you run it though, just let me take a step back and tell you something I forgot to mention before. So this plot right here, each one of those box plots are including all the information from 4 different locations and all the 4 different reps. It's just grouping by rate, which basically it's including everything else that's not rate, right? So this box plot here has data points from all locations that at this rate, all locations, all reps. So now if we wanted to look at how those box plots are for different locations, we can just add that fill on the box plot and look at what happens, right? So now it took each one of these big box plots up here and broke that down into different locations and gave each one a different color. So we can kind of see what's going on. And this is really interesting, right? So this is just data exploration. There's no analysis at this point. We're just looking at the data. And I can kind of see a pattern here. Can you guys? So what I see here is basically at 2 locations increasing. So as you increase the potassium rate on the X, doesn't really seem like potassium concentration on soybean plants is increasing that much. It's almost even seems like it's lowering for the blue side here. And the red perhaps, but the distribution of the data gives an idea that, I don't know. And there's this other group here, lower here, these 2 sites, these 2 locations that seems like increasing potassium rate is actually increasing the response that we're seeing on that box plot, right? So, this is useful, but we can do something else to it to help us see those differences by location. So I want to ask you to copy this ggplot code here that we just did and paste in the following chunk. And then at the end of the parentheses, add a plus, and we're going to use a function that's called facet. Facet underscore grid. And then inside of the function, I want you to write a dot and then a tilde and type location, which is the column name that has the location information. So if you run it, you're going to see this. So what the facet grid function does is basically takes the variable you're facetting over, looks at the levels of that variable, and creates a plot for each one of those levels. So because we chose location here, it basically created a plot for each one of the locations. This is super useful with something I use a lot when I'm doing graphs, because especially as you start getting data that's more complex, you're going to start having more variables. And if you make box plots, just like as we saw up here, so it basically came from this big old box plot to really understanding what's going on visually, at least, in each one of the locations. And this is all the same data, right? It's just that we're using variables to separate them and create groups that make sense visually. Okay, everybody together? Right. Okay, so again here we kind of see that, like at least I think there is this pattern visually that there are two sites that even the zero potassium, like where they did not apply potassium, it's pretty high already. Like the plants already have a pretty high concentration, so A1 and S1. Even when they did not apply fertilizer, the plants had a high concentration already. And there doesn't seem to be much of response after that. And the sites where the soil was or had less, well, I don't know. We don't know about the soil at this point. I'm just implying, I guess. But let's just talk about what data we have. So when we did not apply fertilizer, we see that the zeros started lower, and the concentration in the plant increases as you increase the rate of fertilizer. So it seems like we have these two distinct groups here as far as response to fertilizer. But that's just visually, right? We don't know if this is statistically significant yet. Okay, so let's get into the analysis of variance. Yes.
Because I think they didn't have the entire code, so they won't need the part for the ANOVA, right?
No, but yeah.
So you can start from now.
Yeah. Thanks, Lou. Okay, so we did a whole bunch of data wrangling yesterday, and I'm still going to do a little bit more today. So I want to invite you to just write here soy K _ W again. We're going to use that assignment symbol, and then we're going to use pipes. So we're going to kind of review what we did yesterday. If you were not here yesterday and you don't know this, you may get lost. But if you were here yesterday, this should make sense. So if you recall the pipe, we're going to start with the data set that we want to start with, which is, so we're basically going to start with the data set and overwrite on the same data set whatever we're going to do now. This is okay if it's just like a small thing as I'm going to do now, but if you're doing a whole bunch of data wrangling steps like we did yesterday, you actually want to save on a different object so we don't overwrite the initial one. So we write the data frame name that we're starting, we use the pipe, hit enter, and we're going to use the mutate function. So what happens here is what I want to, let me just, you don't have to do this, I just want to show you something here. If I go back to this, all right? So our location is being interpreted by RS character, as it's showing there. Our rep is replicate is double, which is numerical continuous. And our rate is also double, which is numerical continuous. So we're going to talk more about the differences between ANOVA and regression, but for now, I just want you to do something that you're going to see why it makes sense afterwards. So we have to transform both the replicate and the potassium rate to factor. They cannot be numerical to go into the ANOVA. You're going to see why later. So for that, I want you to type here F for factor, and then let's just write that K potassium rate _ kilograms per hectare, which is, so this part here is the same as we had before. I'm just adding an F in front of it to say that is a factor. And then I want to use the function factor, open parentheses, and then write inside of it again the potassium rate _ kilograms per hectare. Okay. So now you see how like my cursor is coming back to be within the last two parentheses there. I'm going to add a comma and hit enter. You can see the cursor is still inside the mutate function. So we're just going to do the same thing now, but for rep and for location. So rep I want to call _ F, and then rep equals factor rep. And then again, I bring my cursor in between the parentheses, add a comma, hit enter. In location, I'm not gonna do a F location, and I'll tell you in a second why. I just want to override the old location, which was a character, and now I want to have it as a factor. So the thing is, normally we actually normally R reads text and interprets that as character. However, we always want to have them as factor when we're going to run analysis, because sometimes that makes a difference, and the factor is the way that we want it to be in when we're running that. Okay, so let's just run this piece of code here, and I'm just going to print that data set that we overwrote here so you can see what's going on. So we still have the location. So now location, you can see, is a factor. Now rep, because we didn't overwrite on rep is still there, it's still a double. But now if we come to the side here, we're going to see that we have an F rep that is a factor now, and an F K rate that is also factor. So if we had done this before on that box plot that we use factor location, or sorry, factor K rate, we could have, if we had done this before, we did not have to use the factor, the function inside ggplot. We could just use this column name here. Just to show you that sometimes if it's just on the go, on the fly, you can use the factor inside ggplot, but that's not saving to the data frame. So I actually have to create that variable outside of ggplot and save to the data frame. And let me tell you this. So if you got to this point, I want you to add a pipe to the end and hit enter. And so here's what happened. So I had this data set and I ran this entire script beforehand, and I realized that there was one block in one of the locations that was causing some convergence issues on the model. So I decided just to remove that block, which basically means we're removing 4 observations from the data set. And I want to show, and well, I have to tell a little bit more about that. The reason why I removed it is because the model wasn't being run. And if it was my data set and I was doing this analysis for me, I will look more into it, try to understand what was going on to see if it was a specific observation, if it was a typing error or whatever it was. But in this case, I just wanted to get it out of the way so I could show you how you would do normally things if you didn't have issues. Okay, so if it comes to your analysis and you have some data points that are not behaving well, the model is not working, you really want to investigate why. You don't want to just blindly remove that from the data set because that's wrong. But that's what I did here just for sake of time. So basically, it's location W1 and it's the rep 1. I want to only remove those 4 observations. What function do you guys think I'm going to use that we saw yesterday? Select? Anybody else has a different guess? Filter? Yes, so it is actually filter, and the reason why is filter works on rows and select works on columns. So select, you basically select the entire column without knowing what's inside of it. With filter, you can also say I only want the rows that have this specific condition. So let's use the filter function here. And the way that we do that is, so I say location. So let's do this. Let's just first do location equal, and then open the quotation marks, W1. And now after this, you can just hit space and then add a vertical bar. Hopefully you can find that easily on your keyboard. And then, because we don't want to only remove everything that's that location. We want that location, but only one of the blocks. So now we're going to use the frep column that we just created. And we're going to say equals to open quotation and close quotation marks 1. Okay, so don't run this yet. The thing is, if we run this, what's going to do is it's going to actually select only that location and that block and give us 4 rows back. But we actually want to exclude those and not only select those. Or sorry, I'm using select, but I shouldn't. Not only filter them. So how do we tell R that we want like the opposite, like that, but the opposite of that, right? So we basically come back to this equal sign, and you delete the first equal sign, and you add an exclamation point in both cases. Okay, and then if you run it and you print soy K, you're going to see now that it has 60 rows instead of 64 because we removed 4 rows that were from location W1, block 1. Okay? Okay, so I guess now we're basically ready to run our model. Okay, so here this first line of the next chunk is just changing the matrix restriction or the contrast type that's being applied to the matrix of the design. This is way too complex to explain now, but so you just have to accept it, I guess. There are different restrictions, and the one that we want to use normally is the sum to 0, which is what we're setting here. And the default in R is not the sum to 0, is the set to 0. They're a little bit different. They can be important sometimes, depending on what you're doing. I just have the habit of changing it every time I run a model. So you can just run that, and that's going to change the default behind the scenes. It doesn't tell you anything back. And now let's build our model, okay? So I want you to call this soy K underscore mod. Use the assignment symbol. And we're going to be using a function called LMER. So this function is coming from the LME4 package. And who here uses SAS, uses Glimix or mixed in SAS? Can you raise your hand? No one? Okay, great. Don't even have to explain that. So what we're going to do is, the way that we tell the model here is basically starting with the response variable, the thing that we measure on the field that we want to try and explain using our treatments, right? So that's K underscore PCT. So this is going to be our response variable. You add a tilde to say what you're going to use to explain it. So this side of the right side of the tilde is basically the information that, like, your treatment design. So what we're going to use potassium rate and location here. So you can just go ahead and write location, and we can do a plus, and then use so here's the point. Here in the data frame that we're going to use, we have both potassium rate as numerical and as a factor. We want to use the factor one here, and you'll see why in a second. So we're going to use the FK rate underscore kilograms per hectare. And so I just want to quickly show you a notation of models in R. I think it's a little bit different from what SAS does, perhaps, but it's basically, if we use a plus, it's just going to do main effect of location, main effect of potassium rate. If we want to have the interaction as well, we have to write the following thing. So we add another plus, and then we say location, colon, potassium rate. So this is, we're calculating main effect of location, main effect of potassium rate, and the interaction between them. However, there is a shortcut here, and here it is. If you just delete what we just wrote here, the location, colon, potassium rate, you just delete that, and you come between location and potassium rate, and you add an asterisk. So the asterisk notation is basically making the main effect of both and also the interaction. So let's say if you had another variable, let's say, I mean, we don't have here, but let's say that we had, I don't know, ear. If you did this, so by using the asterisk, you would get all the 3 main effects, all the 2-way interactions, and the 3-way interaction, all by doing just the asterisk, okay? So just to let you know. So you can just leave like this for now. So location, asterisk, potassium rate. And now we're going to add a plus. And here's the thing. So who here has already had experimental design courses? Can you just raise your hand, please? Just so I have some idea. 1 person, 2. Okay, 3. So I'm just going to, this is more complicated stuff that I really don't want to spend too much time explaining, because there are courses that are semester-long courses that you have to take to understand this. but I just want to show how to do it. So whenever you take a class, or maybe you want to learn yourself, you at least know what is the code that you can use to implement that. So in randomized complete block designs, I'll just do a quick demonstration here of why one would use RCBD. So RCBD is randomized complete block design. It's probably the most common design in field studies in agronomy, but it's not the simplest one. The simplest would be the completely randomized design, CRD. Okay, so a CRD, basically, let's say you have this area and you believe it is homogeneous. You just break down into plots, and then you have your treatments, and you randomize the treatment to the whole area. So you have no restriction on randomization. So let's say if we have three treatments, 1, 2, and 3, because of the randomization process, it is possible that you could have treatment 1, 1, and 1, and don't have any ones on the other side. That's possible because of the CRD design. However, let's say that you know that this part of your field here is sandy or sandier, and this is more of a clay site. So you know beforehand there are very clear differences in that study area that will likely affect your yield in the end of the season. So then we come with randomized complete block designs. So we create blocks. In this case, you can think of each one of these columns here as a block. We create blocks of homogeneous plots, and then inside each block, we take all treatments and we randomize inside of the block. So let's say we would never have 1 and 1 together on the same column, because this column is a block. So we would have 1, 3, 2, maybe 1 is again here, maybe there. But each treatment appears only once in each one of the blocks, and you're controlling for variation that you know exists in the area. This is basically what an RCBD is. And normally, I guess most often than not, when people do RCBDs, randomized complete block designs, they treat the blocking effect as random. And the case here is the following. So probably, I don't know if you who here has ever analyzed an RCBD for your own studies? How many times was the block factor significant in your ANOVA? Sometimes? Like for me, I think like 90% of the times block is not significant. What that tells you is you don't have to block. However, in agronomy, we most often than not, we block, even if we know there is no variability. I mean, there's always going to be some background variability, right? There's always going to be there. But even if we don't think that our area has 2 distinct soil types, or maybe a drainage different way that's causing differences there, even if we believe our area is homogeneous, we still do our CBDs for different reasons we're not going to talk too much about. And then people, so when we're running models, we also have the distinction of fixed and random variables. Do you guys know what that means, sort of? No? Okay, so quickly on that as well. So if I ask all of you your height, right? And I create, let's say, a histogram where I have height here, and then I have frequency. And then I have all of our data points, and I create this let's say like a histogram density plot that looks like this, right? So there are a couple different things that we can extract from this distribution here. One of them is the mean of the distribution, which is likely going to be right in the middle, right? So here's the mean of this distribution. However, maybe I don't really care for the mean. I want to know more the variance. I want to know how variable you guys are as far as height. So maybe I don't care about this value here. I actually care about some value that gives me this distribution here. So basically, if you think about it, your treatment effects, the things you're applying are fixed. You want to know the average of whatever you're measuring that's being caused by that treatment. And in RCBDs, we assume that most of the times people assume that blocks are random, which means that you don't really care to know what is the average yield in a block. You really want to know what's the variability within the block, so you can use the variability on your standard error estimates for when you're comparing means. So that's basically what the difference between fixed and random is. Okay, so here, the way that you specify fixed effects in a model in R is just by calling it by its name, like we're doing here. So location is fixed, potassium rate is fixed, and now so if you have one randomized complete block study, let's say if we just take one of the locations, block would be random there. So it would be, like rep would be a random variable. However, now we're going to analyze this entire data set with 4 locations together. So that's called multi-location or maybe multi-year or maybe multi-environment analysis. When you have those situations, so we have the same design, same experimental design, same treatment design replicated over time or space. If you want to combine all that data analyzed together, you have to nest your block within in this case, location. If you have different years, it would be year. If you have different locations and years, it would be the interaction between location and year nested with, or the wrap nested within that, that environment. And this is how R at least understands that nesting structure. I know this gets really complex on the stats. You may not be understanding what I'm saying, but I just want to tell you why we're going to write this. So on the syntax of LMER, the way that we tell that something is random is you open parentheses, you type 1 inside of it, you add the vertical bar, and then you add the variable that is random. So if this was one location only, we would say rep, like that, or actually frep, the factor one. However, because it's a multi-location data frame, we're going to use location and then / frep. So that's how it knows the rep is nested inside location, and that's how. And this is important. In many studies, sometimes should treat things as random and don't, or the other way around, and that can cause some differences in your inference when you're actually extracting means and doing pairwise comparisons. Okay, so the last thing that we have to add here is the data frame. Yes?
What would happen if I just grab
So in that case, I mean, it would run, and that's the thing, right? The problem with models is that it runs, it gives you something, but you have to know what you're asking it to do. So if you just put rep there, it's basically going to calculate one random intercept for each one of the reps, assuming that they are independent, or assuming that they are all within the same space, let's say. But you know that they're not. You know that these 4 reps came from a location that may be totally different from the other one. You don't want to just group them without having that nesting structure. Okay, so I want you to come here in between those last 2 parentheses, add a comma. You can hit enter just to make it easier to read. And that's just, there's an argument here that's data. So we just have to say what is the data that has all this. So if you recall, it's a soik_w. So your model should look like this. It should have location, asterisk, F, potassium rate. So it should be the factor and not the continuous one. Plus, and then you tell the error structure of a random effects, location, / frep, which means that frep is nested in location and they are considered as random effects in your model. And that's why we're using LMER. So if you use mixed and if you use Glimix in SAS, this would be about what that would be in SAS. And if you had a study that was a completely randomized design, did not have any random effects, in SAS you would use proc GLM. Here you would use LM, so without the ER. So that's why we're using LMER. So if we just run this, it does give us a warning here, and you're going to see why that is maybe in a second here. For now, you can just ignore that warning. You're all probably going to get that warning, but we're going to see what this is in a second. Okay, so now let's run the ANOVA on this model. I want you to use the function ANOVA with the uppercase A. There is also an ANOVA function that's lowercase, and this one comes with R without you having to load any packages. The uppercase ANOVA function comes from the package car that you installed and loaded above, and we really need this one, the uppercase A, because they're applying different types of sum of squares, which is another mess that you don't have to really know much about. It's just that the type that we want normally is the type 3, and the lowercase ANOVA applies only type 1, and sometimes that can give some problems. So let's just keep it consistent, always use the uppercase ANOVA. So here, the first argument that it takes is the model, so it'll be the soy k underscore mod. You add a comma, and then it has an argument for type. You want type 3. So that's the type 3 sum of the squares that we wanted to apply to our model. So if we run it, ooh, look at that, ANOVA tables. Okay, so here I want to stress a point here that's going to be really important. So we have an intercept, which if you've taken a design class, this would be your overall mean. And then we have the effective location of f of factor potassium rate, and then their interaction here. So the interaction, again, is shown by the colon between those two variables. And so let's look first at the p-value. So everything is significant. That's always interesting. And look at the df, degrees of freedom. Okay, so if we look at the potassium rate row, it has 3 degrees of freedom. And the reason for that, I'm not going to get too much into it to not spend too. Sorry. All right. So I'm not going to spend too much time, but basically what it's doing is it's doing how many levels we have. So we have 4 rates. So we have 4 levels minus 1, right? So it's going to waste or spend 3 degrees of freedom to calculate the coefficients for location only. And the total number of degrees of freedom is the total number of observations you have. So here's why it's important that yesterday we talked about how we use the class function to check the variable type and to pay attention on that. Because if we had used the k rate instead of the fk rate, so if we had used the numerical one, we would have only 2 degrees of freedom here. And the reason why is this. So if it is a factor, it doesn't care that those are numbers, right? It could just, the 0, 56, and so on could just be A, B, C, D. It wouldn't matter for the analysis if it is a factor. Because then what's doing is calculating a mean for each one of those 4 levels. If instead that variable, you enter the variable in the model as numerical, which is the k rate without the f, you would not try to calculate a mean for each one of them. You would actually try to fit a regression. So let's say if you have a plot. So like we have that plot here with k rate and the 4 rates. And let's say we have the data points like this. If you enter k rate as a factor, it's going to calculate this mean here and give you this mean. If you enter that in the model as numerical, it's not going to care about those means. It's going to calculate an intercept and a slope. So it is still calculating something, but it may not be what you want. And this is the main difference between ANOVA and regression. So in this case, our x variable could be either categorical or numerical, depending on what you want. Do you want to know the means, or do you want to know the response overall? And we're going to see more of that later tonight. So that's why we have here as factor. Okay. So how do we know this is a good model? We have to check model assumptions. So every model has assumptions, and you have to check them to make sure that you can use that model to calculate means and make comparisons in the end. So you can run any model if you want, as long as you know how to tell R how to do it. But if you don't check the model validity, R doesn't know that. It's still going to let you calculate means, make pairwise comparisons. You could be totally wrong. Your model could be really, really bad, and you would never know if you don't check it. So that's what we're going to do with the model assumptions checking is we want to make sure the model fits the data reasonably well. So just an example for you. So again, if we have potassium rate and concentration, right? Now let's say, this is not our case, but let's say it starts like this. You have lower concentration, and then as you increase the rate, you increase the concentration, and eventually you start decreasing. So it's clearly quadratic, right? So the model that fits it is this. However, if you don't fit a quadratic model, if you just fit a slope and intercept, you're going to be fitting something like this, right? And clearly this model here is wrong. It does not fit your data. And you know if the model fits your data well or not by looking at the residuals, which is what we're going to look now. Okay, so if you come here on this first chunk on model assumptions, I want you to write, create an object called soyk underscore mod underscore AUG, aug, for augmented. So you use the assignment symbol, and then I want you to use the function augment, and then within it, I want you to write the model object, which is soyk underscore mod. So this function augment comes from the Broom package, and you're going to see here in a second what it does. So if we print this, so pay attention here that we actually did not give the data set. We gave the model object, right? The soyk underscore mod. And what this function did is basically retrieved again the data frame that we gave to the modeling function. And if you scroll this to the side, you're going to see that now we added a whole bunch of columns. So there's going to be a fitted, resid, cooked, fixed, mu, and a whole bunch of others. So these are all some calculations that it did in the background for us to look at the residuals and how to interpret those. So the only thing that this function doesn't give you is a standardized residue, which usually is what we want to look at residuals. So we're going to add that manually here. So we're going to call again the soyk underscore mod underscore aug, so you can just copy and paste the name from above. And we're going to create another variable inside of it. So to do that, we're going to use a $sign, and I want you to write .std resid, like that. .std resid. So use the assignment symbol there. And then there's a function that's called resid, like this. So the first argument we want to give it is the model again. So soyk underscore mod. You add a comma. You can hit enter if you want. And then there are different types of residuals that it can calculate for you. We're going to use one that's the Pearson. So you say type equals, open parentheses, Pearson, all lowercase. Add another comma, hit enter, and then there's another argument called scaled. We're going to say scaled equals true. Okay? So then we run that. So what that's doing is calculating these values here and saving on a new column on this data frame that we had, and we're calling that .std resid. Okay? All right, so who here has heard of or has ever done residual, like model assumption checks using residuals? Or has ever seen that? Have some idea of what we're talking about? 1, 2. Okay, so let's create a plot, and I will tell you what we want to see first. So let's use ggplot. Start the ggplot, and then we want to use this data frame that we just created up there. So the soyk mod aug. You add a comma there, use the AES. And now, I just want to come here and use the names function just so we can see what are the names inside, or what are the column names inside this object here. So on the X, we want to have the dot, let's see here, dot fitted. So you can just copy that without the quotation marks. If you recall, in ggplot, usually we just use the name without quotation marks. Add a comma, Y equals, we want that to be for Y to be the dot standard resid that we created above. And then you add a plus to the end of that first ggplot row. You hit enter. We're going to add the geom underscore point function. I want to add the AES function here, the aesthetics function, and I want to color the points by location. Then we add a plus again. I'm going to add a geom that's going to be new for you. You're going to see what it does in a second. Well, you know what? Let's just live like this for now. So just remove that last plus that I told you to add. Let's just run this and see what happens. So this is a plot now that we have the fitted on the X, standard residual on the Y. And normally, one of the assumptions is that your residuals the mean of the residuals is 0, there's not going to be any, so they have to be homogeneous. So you don't have like, sometimes, let me just make a quick drawing here. Especially, well, so I worked with nitrous oxide on my master's, and nitrous oxide is a handful for stats because it is really messy and you have to do some cool stuff to work with it. So in my case, so these residuals here actually look okay. So what do I mean? So this plot, right? So we have 0. So we want our residuals to be like randomly scattered. Like you don't want to see a pattern. What happens is, let's say if you have your model, remember the model that I showed you that we have K rate and then K concentration, and the data was clearly quadratic, but it would fit a linear model to it. If you remember this, if you calculate the residual is basically the difference between the model you're fitting, so the line, difference between the line and all the points. That's what residual is. So if you plot the residuals of this analysis here, it's gonna show you a clear pattern. It's gonna be like, you're gonna see that quadratic response on the residuals. And that's showing that your model is wrong, it's not well specified. Which means I have to go back to your model and rerun a new model, maybe with new variables, maybe with transformations. So if we come here, we don't really see any strong patterns here. You know, I see that locations are kind of separated, but there's no like parabolic pattern or anything that really calls my attention. But one of the assumptions also is that the residuals have a mean of 0. And if a residual is larger than 3 or lower than -3 on this scale here, on the standard resid scale, it could be an outlier, which means, let's say, I don't know, let's say that you have a nitrogen study out at the Conza Prairie, and then on one of your studies, a bison came and, I don't know, either ate your study or maybe did something that really changed the response of that study. But you still collected yield, and then you have a data set that's really different, right? So that's what's called an outlier, and we find outliers using this. So it's going to be helpful for us to have the 0, 3, and -3 as lines on this plot for us to visually see how things are going. So let's add that. So you come to the end here, add a plus, hit enter. Let's add a geom age line. And if you hit tab, it's going to give you the options it has for arguments. We're going to use the y-intercept. And because we want to have 3 lines, we're going to use the concatenate function, so the C function. And we're going to say -3, 0, 3. And I want to, so I add a comma after closing the C function, and I say color equals orange, just to make it easier for us to see it. Okay, so let's run this. So the data didn't change, it's just that now it has those visual limits for us to look at and see. So it looks like everything is spread around 0, so that's good. That's one of our assumptions. Nothing is above 3 or below -3, so that's great as well. And another trick that I like to add here is, so if you come back to your ggplot, you add a plus there, hit enter, and type geom_smooth. So the geom_smooth function is going to add a smoothing line to your data. It's going to use a less function to smooth your data. And you don't really have to know what that is, other than that's going to, if your data goes up and down, it's going to try to go up and down with it. And what I like to see in this plot is that, so the blue line here is the smoothing line. We see that is exactly on top of 0. That's great across the entire x-axis. And also the standard error of this smoothing line is all within 0. So that is all indication that this model fit really well our data. So we're good. We can basically go ahead and make inferences on it. So I have some other code here to show how to check some other different assumptions of the model. I think we're starting to run a little bit late. So I'm not going to show you them. I'm going to send you on the script. So you're going to have them to check afterwards. But I'm just going to skip and I'm just going to tell you that after checking those assumptions, everything looked okay. So after that, I decided this model is good for my data. I'm going to extract means and do pairwise comparisons. Okay. So you can basically skip to this number 5 here. Oh, something else. So you can stay there on number 5. I just want to go up to show something. So if we go back to our ANOVA here, we see that the main effect of location was significant, the main effect of potassium rate was significant, and the interaction was significant. So how do you look at an ANOVA table? In an ANOVA table, you always start from the lower part of it and go up. So you first look at your most complex interaction. If that interaction is significant, it means you have to break down that interaction. You cannot just, let's say in this case here, our most complex interaction, there was just one, was significant. That is telling me I cannot go and look at the main effect of location alone or the main effect of potassium rate alone, because they are interacting with each other. So I cannot do that. I should look into the interaction itself. So I'm going to go back to 5. This is basically how you decide how you show your data, the results of your analysis, right? So if I'm just going to go back again to show you here that if this ANOVA here was showing no interaction significant, but it was showing only a location effect was significant, what I would do is I would only extract the means for location. I would basically ignore the potassium rate because the analysis said that it was not important, right? So in this case, because interaction was significant, that's what we're going to break down. So coming back here to 5, I want you to write soy k underscore means underscore lock rate. So kind of like that. I mean, you don't have to write exactly as I'm doing. It is helpful if you do, just because then you're going to keep consistency. But, you know, that's like with the upper cases and all that, but that's how I'm doing. So we're going to use a function called EM means. That stands for expected marginal means. It's going to extract the means from our model. Okay? So the first argument we give it is the model object, which is soy k underscore mod. We add a comma. I want to hit enter. You can add a tilde after that. And now we're going to say how we wanted to extract the means. So what I want to do, so if you recall, our model variables were FK rate, kilograms per hectare, and location. So let's do this. Let's do FK rate, kilograms per hectare, and then use the straight bar, and then location. So let's do this. So if we run this piece of code here and we just print the object that we created up there, you're going to see that it basically went inside each one of the locations and created the means for each one of those rates. And it did that separately for each one of the locations, as you can see on my output here. Let's say that, and this, you would do this if you're really interested in comparisons inside the location, and you don't really care if 0 here is equal or not to 0 there. Like, you just care the rates inside a given location. This is how you would do it. If you like to have all, so, and this is important here because even though we're just asking for means, we're not asking for pairwise comparisons. But if the next thing we're going to do is to ask for pairwise comparisons, and that's going to use this structure to give the comparisons. So let's say if we wanted the means and the pairwise comparisons to be done for everything together, so all rates, all locations, all in the same thing, we would use the colon symbol. So it would be like that. And then when you print, you're going to see that now is one whole block altogether. It's not separating anymore the different rates within a given site. And let's say we just wanted to get the means for the rates. We would just delete that colon location, just do the rates, run it. It would give us the mean. It would average over everything else except rates. So here is basically, so you look at your ANOVA, you see what is significant up there, and then here is where you tell it, based on the significance of the ANOVA, what do you want to extract. So here, again, I just want to keep that FK rate within location. Okay, so I want to ask you to do that as well. Just run that and get our results. And now please go to the next chunk, which is the pairwise comparisons. Okay, so here I want you to call this soy K underscore PWC, which stands for pairwise comparison, underscore lock rate. Use the assign symbol, and the function that's going to do this for us is the CLD. It stands for compact ladder display. It doesn't make too much sense, but that's what it does. So here we basically tell what the argument that it takes is the E and means object that we created above. So if you just go above, just want to close this to not be too long, and you just copy that E and mean that you save the E and means into this object. So just copy that object. You come down here and you give it like that. And then you can just run this, and you can just print below here to see what happened. Guys, this I don't know if for my master's I use SAS, and SAS has something similar to this, but I don't really like the SAS option to do. So what I would do is I would get the means. I would get a table of all pairwise comparisons between all treatments. I would see what treatment was the highest and the lowest. I will look at each one of the p-values, see if it was below or above 0.05, and then start giving ladders. This is a nightmare. This is something you don't want to ever do manually because it's easy to make mistakes and it's just a pain. So here, look at this. So now R basically added this column that's called dot group, and here is the different numbers are telling you the statistical difference between groups. So if you look at location A1, everything is the same, kind of like what we thought. I don't know if you guys remember, but when you look at the box plots, A1 was pretty stable up there. Now O2, there are some differences there. S1, no difference. So is it the other side that was up there? In W1, some differences as well. Cool. So you don't have to do this manually. Sorry. Yes.
What's the meaning? 1 and 1, 2, 2, 3.
So every time that you look at two means and they don't share a same ladder, that means they're statistically different at 0.05 alpha level. Okay, so this is the basic CLD function. However, there is some stuff I like to do it to make it more friendly on my output at least. So you can just give it the E and means object like we did. Now I want to ask you to come back here, add a comma, hit enter. And so you can stay there. I just want to show you something on my screen. So below here, it's telling me that it used this Kenworth-Roger method for degrees of freedom approximation. You don't have to worry about that now. That's kind of complex. The confidence level was 0.95, which means the alpha was 0.05 or 5%, which is the most common one used. It is telling me that's using a Tukey method to adjust the comparisons. We're not going to get much into that today, but it's just making it harder for something to be significant as compared to not using Tukey. And it's showing alpha below here as well. So, this really depends on your area. There are journals that people will report mostly unadjusted pairwise comparison means, which means no Tukey. It's just what we call Fisher's least significant difference. So I want to show you how to change that to not using any adjustment. So there is this argument called adjust. Then you have to say none like that. So that way it's not going to apply Tukey adjustment. So it's going to make it a little bit easier for you to find differences. We can talk for a whole hour about what that does and if that's cool or not and when it's cool or not, but we're not going to do that now. Also, something else I like to change is the default is to add numbers to differentiate. I really don't like numbers. I prefer letters. So he has an argument that is letters uppercase. So you can just do that, and R already has this object called letters lowercase in its memory that is going to know what to use. It's going to use A through Z all lowercase. So you can just specify it that way. And also, usually the way that it assigns letters, I think it's not the order that I like. It's either like it starts high and goes low, and I want the opposite normally. So I just, to change that order, we change this argument here, reverse equals true. So once you run that, it should run with no problems. And when you print it, I mean, the main difference you're going to see visually here is that now instead of numbers, you have letters, and it's starting from the highest, or from the highest value within a given site and going to the lowest.
Just one I was having some error, but it was requiring one more package that was multiple view. If someone is having the same
Good call.
Error, you just need to install the package, which view.
I'll show that here.
Probably is showing there.
So yeah, thanks, Lucas. That's a really good point. I would not have caught that. So you can use the install packages function. You use the quotation marks. Well, you know what? Let's not do this. Let's instead go through here, because I don't remember. I know that multicomp view has some uppercase in the name.
Yeah.
So since I don't know that, I'm going to come to the packages tab. You click on that install button up there, and here you can type multicomp. Yeah, so that's multicomp view with the V uppercase is what you want to install if you were having issues as well. So you can just go ahead and say install. And that should have fixed your problems. Has anyone else, I know she was having issues, is anybody else having trouble with running the COD function? You are? Can you? Thanks, Jose. Jose's going to help you out. Okay, so let me see what I have here. Oh, okay. So what I want to show you guys basically is that if you, so this object here that has the means, the model means, the ladder separation, it's not a data frame. Like you don't have to check if you don't want. I'm going to check just because I'm curious, but it's certainly not a data frame. So it's a summary EME, and it is a data frame, but it's really not, right? So if you try to use this object in ggplot, it's going to say this is not a data frame. So let's transform that into a data frame, which is super simple. I just typed the same name there. I use the assignment symbol, and there's a function called as.data.frame. And then inside of this frame, you just paste again the same name of that object. So once you run this, and we print again the same object just so we see how it looks like, you see how now it is an actual table. Like it's not like grouping within sites and giving all that structure that we saw before. It's an actual data frame. So this is what, okay, so let's just recap for a second here what we did. We started with that supermassive data set yesterday. We brought that in. We looked a little bit at some plots. We did all the data wrangling, got it to a stage that we thought, okay, this is what we need to do better plotting and to do modeling around the ANOVA model. So now we use that wrangle data frame. We did we did a model first, and then we checked the model on ANOVA to see what was significant. We checked the model assumptions. It was everything all right. Then we extracted the model means, which are different than if you just do a mean on the raw data frame. I mean, it could be different, depends on the situation. But when you show means on a graph for publication, you want it to be your model means most of the time. And now we created the ladder separation. So we have everything we need to make a super nice plot with the results of this analysis, right? That's something that you could publish somewhere. Okay, so let's make that plot. So this first bar plot here, I want to skip that just because it's a little bit more complicated and we're running short on time. So let's go to the box plot means, which is going to be the simplest one. I'm going to send you the script later. You're going to have all the code so you can run that. It's going to be reproducible because you're going to have the data and the code so we can do that yourself. But let's come back to the box plot means chunk. All right. So we're going to start a ggplot call. The first argument again is a data frame. I'm sorry. Hold on. Actually, the box plot is the most complex one. Let's do the bar plot. That's going to be the simplest one. So, sorry, go up on that bar plot means, not the box plot means. We're going to be doing that. So, ggplot call AES function. So the first thing that before the AES function, we need to tell it what's the data frame name, which is this one that we just created above. So the soyk PWC lock rate. So we tell it to the ggplot. Now we call the AES. So let's just check the column names of this data frame that we're using here. So on the x-axis, we want to have that factor potassium rate kilograms per hectare variable. On the y-axis, we want to have the potassium percent, but now because these means are coming from the model, the way that the model calls them is EM mean. So this is what is actually our potassium concentration, which is our response variable, right? So if your response variable was yield, that's what would have been called here in the data frame EM mean. Okay, so at the end of the ggplot, just add a plus, hit enter. We're gonna add this geom underscore bar to add a bar to this plot. Inside of this, I want to use that AES function. So AES, open parentheses. I want to say fill equals location. Okay, we can just run this very quickly just to see what happens. It did not work, and the reason for that is the following. So geom bar is one of the geoms that need you to tell what to do with different values, because it's seeing a whole bunch of values there and it doesn't know what to do. So we have to say, so outside of the statics function on geom bar, you say stat equals open quotation marks identity, like that. So once you do that, it should run now. Look at that. Kind of ugly, I guess. We don't really want to show all locations stacked on top of each other, right? So let's do something right away here. If you guys remember, we used the facet grid to split things based on a given variable. Let's use that. So let's use the plus right after here, and then say facet underscore grid. Then you say dot tilde location, and then run. Cool. Okay, so now it did that for us. You know what? Let me ask you to change one little thing. So there are a few different facet functions. We have been using the grid. I actually want to use the wrap. So change the grid for wrap, like that, like a burrito wrap. And run again. So it's just going to change how it configures the plots and the position of them, but it's the same, basically the same stuff. Okay, so these bars are specifically for each one of the locations and each one of the rates. And we can kind of see, and it's the mean, right? So we don't have all the data points anymore because it's the mean from the model that we use to analyze this data. So now we actually see that bar is just one value, right? It's the top of the bar is one value. That's how it's plotting it. And now there's some stuff that we can do to make this plot nicer, and some stuff that we can add to make it more useful. So let's start by the usefulness. That's the most important. So I want to add the letters to each one of these columns here. And if you remember, we have those in this same data frame here, and they're called dot group. So what I'm going to do is after the facet wrap, I want to add a plus, hit enter, and we're going to add a geom underscore text. And then we're going to open the AES function inside geom text, and we're going to say label equals to dot group. Okay, so if we run this, that's what it did. So it put the letters in the right places. This is also nice because you don't have to be manually putting letters in Excel or whatever else you were adding them. However, if you look, the letter is actually being plotted right on top of the mean. So that's why it's kind of overlapping with the bar, and I don't like that. So to change that, we can come here to geom text again, outside of the AS function, add a comma. It has an argument called nudge y. So we're going to use that and use a value of 0.3. So it's going to change 0.3 units on the y-axis up that label. So it's getting there, it's getting nicer. Okay, what else? So, so I want to show you guys how I would do this to be ready for publication. So, and maybe, I don't know, you can publish this data here in this type of plot as long as you make it nice, right? So let's try to do that. What do you guys think we can change about this to make it nicer? Like if you want to publish this, what would you change about this plot? Can you say that again? Perfect. Awesome. Let's start with that. So to do that, there is a function called labs. So we're going to add a plus sign, use the labs function. Inside the labs function, it takes title, subtitle, caption, tag, X, Y. It takes a whole bunch of different arguments. So let's say if we want to change, let's change first the Y. So let's say Y equals, open quotation marks. Let's call this plant K, and then say that it's a percentage. So if you can go ahead and do this. And while we're at it, let's also do for the x-axis. So right after that last quotation mark, I just add a comma and I say x equals, and that's our potassium rate, right? So I'm going to open quotation marks again, say potassium rate. This was like kilograms of K2O per hectare. Okay, so I'm going to run this so you can see what happens. Nice. Okay, so it's getting better. What else would you change? Or do you think this is ready for publication, for a journal? The grid? We can do that. So there are different ways. So Carlos said remove the grid. Oh, the gray background, you said? Okay, so there are different ways to do that. I want to show you one that's really easy. So one of the packages I asked you guys to install was GG Themes. What GG Themes does is it has a whole bunch of pre-made themes that change a whole bunch about your plot that you can just do very quickly. So add a plus at the end here, hit enter, type theme _ and then you can just scroll this list. These are how many different themes exist for you to pick and choose whichever one. There was some of them are more useful than others. So let's say I really like I think it's classic. Let's just try classic. So if we just run it, that classic theme well, it's not classic. No, I don't like that one. Let's try another one. So if you just delete classic and leave the underscore, let's try BW. I think it's for black and white. Well, that's a nice one. I like that one. So most of them make some different changes. Some of them are very different. So there's one that's dark. I want to show you the most distinct ones so you can have an idea of what's available. This is the dark one, very different. There is one that is the Economist. I think that's an actual magazine that uses a style of graphs, and they just created that style for you to use here, which in our data looks really weird and not nice. Another one that's different is the Solarized. So if we run that, it has this solarized look to it. Maybe you can't see because of the screen, but it's kind of like tan color. Let's see some other different ones. And the theme that ggplot uses as default is the theme gray. So this is the default that ggplot uses. You don't have to specify because it's going to be already using that as we were seeing. So, you can just play with all these different themes and see what you like. I'm gonna, let's see. I think I'm gonna stick with the BW for black and white. I like that one. You can change a different one if you want. It's really just to get you guys familiar with this. Okay, so something else that I would like to do here. So if you think about it, do we need to have this legend there? No? No, right? It's really not telling us anything because location is already separated by their own plot. So, it gives a nice visual to have the different colors on the plot, but the legend itself, we don't really need it. So let's add a plus there, and there is a function called theme. So here's the catch, the very important catch. This function theme here, if you hit tab, it has a whole bunch of stuff that you can change, a whole bunch. It's just like every single thing you see on this plot, every color, every shape, every size, everything you can change under the theme function. And you would think, well, I can come inside the theme BW function and change all that. You cannot. So you really, even if you don't use a specified theme as we are using here, and you want to change something about the plot is very specific, has to be inside the theme function. So not theme underscore something, has to be theme only. So one of the arguments is legend.position. And it takes the arguments top, bottom, right, left, and none. So let's use none. Cool. Okay, that's starting to look nice. I want to show you something that I changed on mine. I just wanted to be aware that these things exist. So if you come here to the geom bar again, so that we already have up there, I'm just going to add a comma and I'm going to say alpha equals 0.6. So alpha in ggplot language basically means transparency. So I want to make these columns a little bit transparent. Don't want to make them solid color like they are right now. And something else I want to change is I want to say color equals to black. So every time that something, so if you think about it, if you use the geom point, the default point shape that's going to come with it, if you don't change it, you can change the color of the point, which is going to be the whole point. Now a bar actually has a color and a fill. So the fill is what we're seeing. So this color inside is what ggplot calls fill, and then what it calls color is the outline. So I like to have a black outline there just to, I don't know, I think it looks nicer. So we decrease the transparency of the bars, and we have this black outline around the bars as well. And let's see what else I changed here that I want to show you. Oh, something else that also comes with the Digi themes is, let's say you don't really like this color choice that it already gave you. So let's just come here after the theme underscore BW. So usually if you are changing something on the theme that I'm showing here, you want that to be your last row of your ggplot sequence. So everything you're changing, change above it. So let's add something here and start typing scale underscore. So we are going to change the fill in this case. So we're going to fill underscore, and then just look at this list here. All of these are different options of already made color palettes that you can choose from without having to specify manually what colors you like. So I like to use the one that's called Tableau. Tableau is a software that I think it has a palette by default, and our people that made this basically just created a palette inside R. So if you just run that, it's going to change to a different palette. And you can just play around. You can just come back here, delete the Tableau part, and just browse again and check which ones you like. And if there is none that you like, let's say I want a very specific color choice for my different 4 colors, you can use the manual. And then if you come inside, it has this values argument. And because you have 4 different fills, you're going to have to give 4 different values of color. So we're going to use the concatenate function for that. Let's say I'm just going to type here red, orange, blue, and purple. And if you're really, like, if you enjoy playing with colors, like I know I enjoy playing with colors a lot. So you can come and just Google like colors in R. And there are so many of them, so many. Like you're not gonna get bored with colors if you come to this. So, and each one of them have this. So this is the name that you would use. So where I type red and orange, you would type this name here. So there is just a whole list of colors you can choose from. That's a great point. Yes. So one way of telling what color you want is by the name, like we just saw. But each one of those colors also have a hex code, which is like a alphanumerical, I guess, combination of words, of letters and numbers that you can specify specifically what color you want. And that's really useful, yeah, because like if you want to use like the K-State purple in your presentations, that color has a hex code that you can find online, and you can just copy that and paste here. It's going to be the same color on your plots. Great point, thank you. So I'm just going to stick, well, I think this looks all right for now. So let's say we think this is good. You have a question? Okay, so the name of the locations is a change you have to make on the data set itself. So I can show that to you very quickly here. So this is the data set here, right? So the column that is called location. So what we can do is, let me just do this. There's a function called levels. So because location is a factor, we can extract its levels. So if we do that, oops, actually, oh, I forgot to say $sign. So $sign location, and you get the levels of it. It's going to show these 4, which are the actual levels. So let's say we wanted to call them, I don't know, 1, 2, 3, 4, or whatever we want to call them. You would use the assign symbol, and then use the concatenate function because there are 4 values that you have to give it, and then just give in that order. So you have to give in the same order that they appear as when you make the levels call. So it's going to be A1, O2, S1, W1. So you can just say here, I don't know, you can say A, B, C, and D. So if you do this, now you actually, and you rerun just the levels part without the assignment, it's going to tell you that now the levels are called A, B, C, D. And then when you plot it, that's what you're going to see. So, I mean, when I send this script, it's not going to have this because I was just showing. So you don't have to worry about not having the right location names. That's how you would change. And to remove the grid, you would use this theme function here. So I think that we want to add a comma on the end. I think it's panel.grid. Yeah. So we use element line because grid is a line. And then we say, I think it's color equals NA, perhaps. Let's try. Yeah. So this is what I did. And so I know this from head because I've been doing a lot of times. But if you want to change something, it could be. I mean, if you want to learn whatever it is in R, you have to ask Google, right? So just gonna like and a good tip for graphs specifically, because as we talked about yesterday, there are 3 ways of doing graphs in R. So basics, lattice, and ggplot. So if you just say how to remove the grid from a plot in R, it may give you an answer that's related to ggplot. It may not be related to ggplot. So if you want, for plotting purposes, if you're trying to change something on ggplot, you have to be very specific when you ask Google. So I have to say how to remove grid lines from ggplot in R or something like that. That's how, I can assure you there's going to be a handful of posts that somebody asked that, and there's already an answer for it. So this is how you would do it. Okay, so let's just say that this is good, that we think this graph is good. We want to save it to file. Okay. So I was telling you before that the theme function, if you are using it, if you're editing anything within the theme function, you want that to be the last function of your ggplot call. Well, if you're saving it, it's going to be your second to last, because the last one's going to be the saving function. So after that theme, you add a plus, hit enter, and there's a function called ggsave, open parentheses, open quotation marks, put your cursor in between it, hit tab. Again, we are inside the notebook folder, subfolder. So we want to get out of that, go into the main folder. And this is why we have the output folder that we created yesterday. So you go inside this output folder, and now you give it a name. I want to call, let's say, bar means. And then here's the important thing. Here is where you say what is the extension of this file. So it could be PNG, it could be TIFF, it could be SVG, PDF. I usually save as PNG, but like, you know, PDF is a common one as well. So you just, that's where you save basically, is using a dot and extension. And then I usually like to change the width and height because it doesn't look good normally, at least for me, the one that it is default. So I have a width of 6, and I think this is in inches, and a height of 4. So we can just run this. Let me show you again. If you don't have the output folder, it's not going to work. The folder has to be there already, just so you know. And now, just want to call your attention here. I come to the Files tab. This is really, really, it's such a small trick, but it's really handy. So what I'm seeing right here is basically, I'm inside the notebook subfolder, right? So I need to get outside of it and inside the output if I want to check this plot. So to go to the main folder of this project, you click on this R icon there. It takes you there. Go on output. I have some more stuff here from the other things that we were going to see tonight. I don't think we're going to have time. And so that is the bar means. So should be this one perhaps. Yeah. So here you go. Now you can drag and drop to an email, to Word file, to wherever you need to use this. And so like, let's say if you want to play around a little bit with, like, let's just change let's make this taller. So let's make this, instead of 6x4, let's make 6x10 and run it. So here's a very, very important thing. If you want to know how your plot actually looks, you have to save it to file and open that file. Because as you notice, I changed the height from 4 to 10, and here looks the same, right? Did not change. But if I open that bar means, it's going to look very different. So every time you're making a change in the aspect ratio of the plot that you want to know how the final figure looks like, you have to save it and open that file to check it. Okay, so let's just come back here. I just want to keep the 6 because I think that looks nice. And so guys, here's the thing. Yesterday we were a little bit late, but it was because we had some technical issues. We started later. So I think overall we did in 2.5 hours. Today I basically just finished the first hour in almost 2. So we're way behind. I don't think we're going to be able to get to the advanced part today. And this is kind of like, I would imagine that for some of you, maybe most of you, yesterday was already too advanced. And that is really okay, because we really, like all these things I'm showing you is stuff that I learned over 5 years. And we're condensed in 4 hours. So it's really, if you're feeling overwhelmed, that's because it is overwhelming, in fact. So I don't want to rush or to have you here until 9. No, I'm kidding, but we wouldn't. But we don't want to just like keep you here for the advanced part. I'm just like thinking on the go here, but I think that if you guys are interested, maybe we could try to set up the advanced part another day, even like outside of this event that we're having this week. If there's enough interest, we can do that. If you just don't care about it, then we don't have to do it any other time. But this is basically what I think we'll have to do, just because, yeah, I was way too optimistic of how much I could get into an hour, as you can see. So let's do. So I mean, we still have about 20 minutes from our normal time, so let's just use that. Not start the advanced part, but I wanna show you some other things then.
Yeah, just one important thing of that function, that you can choose the DPI, because the 72, the standard, and the journals demand 300.
Good point. So here, there is a DPI argument. So and you said the default is what you said here?
I think it's 72.
Okay, so like you can just change, and DPI is the, what is it? Dots per inch.
Yeah.
Dots per inch. So it's the resolution of your figure. So if your journal that you're submitting a paper requires a specific DPI, you can change that right there. And then of course your file is going to be heavier, but it's also going to look, well, it's going to have a higher resolution. So let me think about some stuff that we can kind of go through now that wouldn't take too much time. So, one thing I want to really stress is, if this is, again, a highly compacted content within very little time. You're not a professional in R. If you never used it before, you're just coming through this workshop, you have not become a professional in R. You're going to have this code as a resource to go back to. That's always great. But I really want to encourage you to, like, if you're trying new things, you don't know how to do, always Google it. Seriously, the community out there is so great. There's so many resources. And usually when I find myself in a situation that I cannot find help on Google, and I think about it, it's probably because I was not asking the right question, or I was not asking the question the right manner. So as long as you can ask a clear question to Google about R, like, how do I do this in R? You're going to find an answer to it. So do use that. Before, let me just let me come on my advanced one, because I had some notes there that I want to tell you. Okay, so basically, I'm going to share with you first. Well, I'm not going to send you the advanced script because we didn't get to start it. So maybe we can, I think maybe Luciana or Josefina or somebody else can send out a poll and see if you guys are interested in another time, do just the advanced one. We can do that. So I'm not going to send you the full script for the advanced yet, but I will send you the full script for the intermediate 2, which is what we just saw now. So you can run that on your own. I'm going to share with you some resources. I just want to show you them very quickly here. So the main packages that we use for plot was ggplot2, and for data wrangling was dplyr and tidyr. These packages are all part of the tidyverse. And the reason why they're all called as part of the tidyverse is because they follow a similar like philosophy of how you call them, how you specify arguments, how things are called within the package. Because in the past, there was like a handful of packages over here that would serve for plotting and wrangling, and another group of packages over here that would do very similar things, but they would not talk to each other. And if you're trying to learn and you're a beginner, you get really confused, because then you use a package from here, a package from there, and nothing makes sense. So tidyverse is basically like they brought together all these packages that are very good together, and they follow the same language, let's say. So I would highly encourage you to use packages from the tidyverse when you're plotting, data wrangling, and other things that we are going to see on the advanced class if we have. Okay, and so so ggplot, tidyr, dplyr, these are all packages that were built by scientists at RStudio. So RStudio is a private company. That's the company that makes RStudio, what we're using here, and is free for us. If you have a company, I think you have to pay to use RStudio if you want to add some extra stuff to it, but that's not our case. We use RStudio for free, and they have a research team that makes packages. So RStudio, as a private company, has a really good documentation of what they do, and they have some cheat sheets. So if you're not American and you don't know what the word cheat sheet is, it's basically like it means like if you are taking a test and you're trying to like peek over your classmate to see the answer, that's what cheating is. And a cheat sheet is basically a place where it has all the cheats. And so they have cheat sheets for different packages that they make. So one of them, so if you just type like RStudio cheat sheet ggplot2, you're going to find this PDF here. Is really handy if you are new to ggplot. It's going to show you all the different geoms that you can use from ggplot. So again, I was telling you yesterday that I have already used ggplot for making all the regular plots, so bar plot, pie chart, scatter plot, all those things that we know about. But I also use it to make maps. So I make actual maps that have spatial data information on the data frames using ggplot. I have made, I don't know, other different types of plots that I don't think of right now, but it's just what I'm trying to say is that it's very, it has so much that you can choose from and use to make plots that I really encourage you to take a look at this cheat sheet here. That's going to give you some ideas of different plots you can use. So that's one cheat sheet. It's for ggplot. As I was telling you, RStudio also makes other packages that we have used. So if you just RStudio cheat sheet data wrangling, they have one as well. That's really good. So if you were here yesterday, we did some data wrangling with functions from packages dplyr and tidyr. They have a whole cheat sheet here showing different functions and trying to explain visually what the functions do. At least when I look at this, I think it's a little bit difficult to understand just on the drawings, but at least you have some idea of what they do. Some of them we used yesterday and today. So we used gather, separate, spread, filter. I mean, there's just a whole bunch of them here that you can look at and have some idea of what's out there in case you need to do something creative with your data. Then there's another cheat sheet I want to show you, which is the RStudio or R Markdown, cheat sheet. So as I was telling you, some people use Markdown. They write papers in R Markdown. That's how they publish. They don't use Word. They don't use anything else. It's basically from Markdown. This is really more complex. If you're just starting with R, I would not encourage you to get into like heads inside of this right now. It's something that as you learn more of other stuff and you want to start integrating your analysis with your reporting, this is helpful for you to know that this cheat sheet here basically shows you some things you can change within the R Markdown. And then the last resource, well, Google is always a resource, so use Google a lot. And then I just want to make some personal merchandise, I guess. So I've been using R for about 5 years, and I really enjoy it. I think you kind of tell. And sometimes I had many people coming to, oh, can you share the code about this or about that, or can you help me with this and that? And then I always did help, but then I realized maybe I'm going to start putting my codes out there so people can, like, if somebody comes ask me how do you do data wrangling, I can just send the link to my blog. So let me show you. Is this? Let's look for it. Yeah. So earlier this year, when I was transitioning from my PhD to my postdoc, I decided to write a blog. I just have 2 posts because then I started my postdoc and I didn't have too much time to write. But these are some posts that I made. So one is showing how to make a map and in R and how to do some different colors and stuff. The other one is about data wrangling. So this data wrangling one here is really similar to the one that we just had yesterday. There's some differences. But as you can see, I had lots of comments, and then I have code and comments and code. And just to maybe hopefully get you excited, this blog here I made entirely in our studio. Like, I never left our studio to make this blog, everything, and it looks this nice. So another thing, if you're using SAS, don't know, I don't think you can make blogs in SAS. So R is just really, really handy, and it has so much stuff. And so I'm going to send you an email then, just recapping with the intermediate 2 script that we saw today. I'm going to send you the links or the PDFs for the cheat sheets that I just showed you. I'm going to send you the link to my blog in case you want to check one of my 2 posts. And if you have, if you want to ask me to maybe have a post, you can try it. Maybe I can do that. Then it would be an incentive for me to do something that I know is going to be used by at least one person. And okay, so I think that was it. Oh, also something I really, really want to ask you guys. So I've given versions of this workshop, like our intro and Digiplot, data wrangling, all that. I think about 4 or 5 times at this point. And every time I do that, I always send a survey afterwards because I want to know what you guys, like, if you thought was useful, if you think you learned something, how you think I could improve next time. So we're going to send you a survey, and I really, really please answer that survey so I know how to make this better next time. I know that you're definitely going to say that it was too much in very little time. You can say that in the survey. I just know that because it is definitely a lot. But I guess the intention is more to get you wet with that. Just to show you and say, here, it exists. If you need to do this, maybe you have to read a little bit more. Here's an example code for you to go off from. But at least you know it's out there. All right? So let's see. And so something that we were talking about is like reproducibility and how that's important. So if I send you my actual project folder with all the subfolders in my project, you will be able, for 99% certainty, that you can run everything I did without even knowing what you're doing. Maybe there's some differences between Mac and PC that I'm not aware of that would cause some issues, but otherwise you should. I'm going to give you the data set. I'm going to give you the scripts in the project and all the folders. You should be able to reproduce everything from zero. And this is what we mean by reproducibility. Now just think about it. If somebody came to you and said, that paper you published, would you mind sharing that data set? I just want to check something. How many of you would be like shaking, like, oh my gosh, that person's going to get somewhere that I never got, or maybe like going to get different interpretation, different results. And it can be kind of scary because if you're not taking note of what you're doing every step of the time, that's really easy for you to forget that you deleted something or that you transformed a column that and then deleted the first one, and then you never know. So this is really the point of reproducibility, and encouraging you guys, if you're just starting with R, it's even better because it can start off with a really great habit of doing reproducible research. So just my 5 cents on that. And I think that's basically it that I have for you guys. So any questions before we?
One thing that would be useful on the graph is the use of superscript and subscript, because it's a little bit different.
Yes. Man, you're like reading my mind. So the thing is, you didn't see it, maybe didn't see, I don't know. But on the intermediate 2 script, if you go all the way to the very lower part of it, okay, I'm going to tell, there's one more thing I want to say after that. So if you come on this lower part, I had an exercise for you. And you can do it if you want. If you don't want, you don't have to. It's really up to you. But it was with that thought of like, okay, let's get you playing with this without anybody else telling you what to do, except this. That like play around with the themes, play around with the scales. And I wanted to challenge you to find on your own how to change the labs to include subscript and superscript, because so if you check here, we will need to have a lower script for 2, and then you could put like Hector and then -1 superscript. So I wanted to suggest that challenge if you want to take it. And then one more thing I forgot is So we talked about why to not use R scripts and instead use R Markdown or Notebook, which you can kind of think of are the same thing for now. But I just want to ask you, so if you've been following along with me and you have all this output printed like on your chunks, I want you to hit preview. It's going to create an HTML file. And I just wanted to show you why I think it's so cool to use this type of file. So, I mean, right now it's just showing a whole bunch of warnings there. But so here is a chunk that created a table. Then you have some plots. They don't look really great at this point, but you can always customize them and make them look better on this HTML file. So, you know, we have everything. So everything that was printed below a chunk is going to show up on the preview of the notebook. So you can kind of see all that here. So just wanted to show you, like, now that we actually have an actual notebook that has some plots to look at, I wanted to show you how you can like see that. So again, if you come on the preview up here, you click on that, it's going to automatically create this report for you from everything. Oh, something else that's nice here is if you come on the top, it has this code option here. If you click on that, you can choose if you want to show or hide code. Let's say if I want to hide, I mean, it's still showing the output. So this is just warnings, but it's not going to show the actual code. You see, like here, there was a code chunk that was showing before. Now it's not anymore. So if you really think about your scripts when you're writing them, you can make them very eligible, even for somebody that has zero knowledge in R. Because you can just send them this HTML, again, opens on a browser. They don't have to have R for this to open this. You can just send them. They're going to be able to see your tables, your plots. If you want to show code, they can see your code and any comments that you add, like I did here. And if you see here, just want to show this quickly. So on my notebook, I use LaTeX terminology, nomenclature, symbology. I don't know how to call that. This is LaTeX basically. That's what you use outside chunks. Like if you want to express something like a mathematical formula or something like that, and you want to use that, this is how you tell LaTeX, and then when it parses into your preview HTML file, then it comes off like this. And just a hint, if you're going to try to use the superscript and subscript on the ggplot, it's not going to be like this, so you cannot just copy and paste. But it's kind of the idea to do something like that. Okay, I think this is what I had for you guys. If you any more questions, any more comments? All right, well, thanks for attending again. Hopefully you learned something from today and yesterday. If you have any thoughts, email me. My office is in Throckmorton. You can come see me anytime. And thanks for attending.